Let's talk about homework 4. Let me talk a little more generally about it first, and then we'll dig into that question in particular. Um, so the homework set was dealing with proofs, and remember, proofs are very formal things. We usually believe what we're trying to prove is true, and a lot of times we can just kind of think about it and convince ourselves easily that it's true, and any reasonable person would believe it's true. For example, if you multiply two even numbers, you get an even number. Well, I mean, it makes sense. If one number is divisible by 2 and another is divisible by 2, their product is certainly divisible by 2. But the fun part about a proof is trying to formalize that, trying to write it up in a way that leads the reader from what you're starting with, your hypotheses, step by step, with each step fully justified, until right in front of them is the conclusion, and they have no choice but to say, oh, okay, that conclusion follows from the hypotheses. So it's about the presentation as much, or sometimes more, than the particular insight that goes into it. And so I saw sort of three classes of issues with the homeworks. The first was proving the converse of something. You're trying to show if P then Q. Some people started off assuming Q and then tried to prove P. And that's a valid proof, but it's a proof of something different. So if you're trying to prove if P then Q, you start off with P and then you try to show Q. The second issue I saw was circular reasoning. And circular reasoning is, prove that x equals 2. Okay, suppose x equals 2. Well, 2x would be 4, and then 2x divided by x would be 4 divided by 2 is 2, so x equals 2. There you go, you're done. But you started off by assuming x equals 2. How can you prove what you started off by assuming? Right? You can't assume something and then, if the sun rises tomorrow, say, hey, the thing I assumed must have been true. Right? That's one of our fallacies. So if you're trying to prove if P then Q, you can assume P, you can do some other stuff, and eventually get to Q. That's good. What you can't do is assume P and then assume Q and then do some other stuff and say, hey, look, I showed Q is true, because guess what? Right here, you assumed Q was true. And as long as you understand that everything after this is only true if Q is true, right? But in the end, what does this proof show? It shows if Q is true, then Q is true. And that is a correct statement. We know that, if Q is true, Q is true. But that doesn't mean Q is true. Right? If I can fly, then I can fly. But that doesn't prove that I can fly. So that's a circular reasoning thing, and I usually put a comment to the effect of, you can't assume this in your proof. This is a thing you're trying to show. So that was another issue. The third issue I saw was not a proposition. And so someone will start a proof and, n is even, n equals 2k, where k is an integer, 6n plus 4 equals 6 times 2k plus 4, 12k plus 4, 12k, 2 times 6k, right? Or something like that. And these are not propositions. Right? This is a proposition. It's a declarative statement. I'm making the statement that this is equal to that. I'm making the statement this is equal to that. I'm making the statement that n is an even integer. But 12k plus 4 is not a declarative statement. It does not have a truth value. Right? Not a proposition, not a proposition, not a proposition. And it's all just about how you're writing it, how you're wording it, right? If you had said 6n plus 4 equals 12k plus 4, you know, and 12k plus 4 minus 4 equals 12k, right? Those are propositions. So those were sort of the three categories that I saw people running into.
Sorry, for the ones that are not propositions, 4, 5, and 6, you just put that in the ignore section and then put whatever's true back into the proposition, or
If this is working through, you know, what you want to do, then yeah, you can put that in the ignore section. But in this case where I saw this kind of thing, I think what somebody was trying to say was like, this was equal to 12k plus 4, and then maybe 12k plus 4 equals, you know, 12k plus 4, and you know, this equals 2 times 6k plus 2 times 2 equals 2 times 6k plus, or something, you know. But every line of the proof has to be a declarative statement that's either true or false.
It's heading in the right direction, though. We're trying to prove that 2 times any number is even.
Mm-hmm.
And we've algebraically worked ourselves into 2 times 6.
Mm-hmm.
Right? Okay.
Yeah, and absolutely, in almost all these cases where I made comments and took off points, I could see where you were going, right? And so you're definitely on the right track. The challenge was mostly about how do you write that up more formally. So let's do that for this particular question. And it's useful when you're doing a problem to start off by saying what it is you're trying to do. So prove that if n is even, then 6n plus 4 is even. I'm doing this from memory, so if that's not the right problem, let me know. So statement 1, let's say n is even, because that's the hypothesis. We're allowed to assume this because we're trying to show if this is true, then that is true. So we can say, okay, let's suppose n is even. Blah, 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 blah. 6n plus 4 is even. Well, we've shown that this follows from that. That's what you're after. All right, n is even. Well, there exists some integer such that n equals 2k. That's the definition of even. A few people tried to use justifications like properties of evens to say that, you know, the sum of two evens is even. There is no such property we've talked about. You can show that, right? But the only thing we know about evens is that if a number is even, it can be written as twice an integer. And so anything beyond that you have to build up. All right. So now we do some substitution. Now we say 6n plus 4 equals 6 times 2k plus 4. And
so where do we get that if it's not from our conclusion? Like, I'm
not making any claim that 6n plus 4 is even. Could be even, could be odd, could be a pink elephant. All I'm saying is 6n plus 4 is the same as 6 times 2k plus 4 because n is equal to 2k. The reason I'm doing that is because I'm looking ahead and I want to eventually show that this is even, so I want to write 6n plus 4 as twice an integer. But doing this is not assuming this is true. And it's a very subtle...
I made that mistake because I pulled that 6n is even. That's part of the hypothesis. This is part of the hypothesis.
Okay.
I care about 6n plus 4.
Right.
And then everything else wrong.
Mm-hmm. Alright, so 6n plus 4 equals 6 times 2k plus 4. And I'm just going to string this out in one big long proposition here and say this is equal to 12k plus 4. And I'm going to factor out a 2. And this is substitution in step 2 in algebra. And then if we want to be really formal, we can say, you know, 6k plus 2 is an integer. And that's properties of integers. That's what we call closure. If k is an integer, multiplying by 6 gives you an integer, adding 2 gives you an integer. Not saying anything about even and odds there, right? Just if k is an int, which it is, then so is 6k plus 2. But now we've written 6n plus 4 equals 2 times an integer. That's enough to say 6n plus 4 is even. And that's the definition of even combined with 3 and 4. And that's what we're trying to show, so that's where we can say QED. How do we know that's what we're trying to show? Because that's what we wrote down as what we're trying to show as the conclusion that follows from this hypothesis.
Is it preferable to do all your subsequent algebra steps in one multi-line step like that? Because I was doing where I was using the commutative property, algebra, and factoring all in 3 separate steps.
As long as it's not going to be confusing to the reader. Now, if you have to do, you know, multiplication of polynomials and factoring and simplification, break it into a few steps. But to go from here to definitely do the substitution and write this, because that's just a substitution. But if you went straight from here to here, that's probably fine.
Okay.
It's probably safe to assume the reader knows how to do, you know, algebraic manipulation of monomials. But some of the ones we'll talk about today, these steps will get more complicated, and it's worth showing those, you know, in smaller sub-steps. All right, another issue that I saw, actually I saw this one a lot, is getting down to something like, I don't know, like maybe you get down to here, well, let me call this not so good. So same thing we're trying to prove. So 1, n is even, n equals 2k. I'll skip the reasons over here. N equals 2k. 6n plus 4 equals 6 times 2k plus 4. 6 times 2k equals 2 times 6k. 6k is contained in integers. QED. Right? The problem with this is you've got the pieces there, but you haven't put them all together. You haven't led the reader from the clear hypothesis to the conclusion, which is 6n plus 4 is even. QED says, which is what we were trying to show. So this proof asserts that we were trying to show that 6k was an integer. That's not what we were trying to show. That's a step towards what we're trying to show, which is 6n plus 4 is even, but this is ending way too soon. Right? You need to take this and you know, do something so that the last statement you make is 6n plus 4 is even, which is what we were trying to show. Well, we do that by showing that you know, 6n plus 4 is twice this thing, and this thing is an integer, and therefore that's even. So again, you know, you've got the steps, but it's putting it together and forming that kind of crystal clear, airtight argument for the reader to follow. And it can feel, you know, kind of silly and redundant with something like this, because, you know, you can probably see the path to the punchline pretty early. But in more complex proofs and in computer programs that have lots of parts and pieces to them, right, it's really important to be able to make this convincing argument from start to finish. And we're going to do this a lot in programming. In 222 in particular, in Winter and data structures, we will develop algorithms which will be correct only if certain other things are true. And we're going to be able to demonstrate that by starting with some hypotheses and working logically and getting to the conclusion that, you know, this algorithm does the right thing. But being able to do that is going to be really critical, because then those algorithms are going to get used to generate code, and that code will, you know, be used to do things like drive cars or whatever. So that's why we're kind of focusing on methodology here.
Sorry, on statement 4, how do you go from statement 4 to statement 5?
So the definition of an even number is a number that can be written as 2 times an integer. And so in statement 3, we showed that 6n plus 4 is 2 times 6k plus 2. And in statement 4, we showed 6k plus 2, this thing right here, is an integer. So those two things together demonstrate 6n plus 4 can be written as 2 times an integer, and that's the definition of being even.
Oh, okay, thank you.
And if you wanted to be more explicit like that, than that, you could say, you know, j equals 6k plus 2, j is contained in the integers, 6n plus 4 equals 2 times j, therefore 6n plus 4 is even. So you can sort of break that down into more pieces.
For questions 4 and 5,
Mm-hmm.
we were supposed to be inferring the conclusion or figuring out a way to argue to a contradiction. And I got a note on my homework for using the contrapositive and then proving that the contrapositive was true. Is that what you're saying earlier is kind of related to circular reasoning, is proving itself there, using itself as justification that it's true?
Yeah, so I remember that solution. So prove P implies Q. So what you can do, and I think what you did in there was you actually proved Q implies P, or not Q implies not P. And then once you've proven this, you can say, well, this is equivalent to this. And so if I've proven this, I've also proven P implies Q. Right? And that's really what an indirect proof is. It's proving if we negate the hypothesis, the conclusion, then we must negate the hypothesis also. But the note was, you know, if you're trying to prove P implies Q and we say assume the contrapositive, well, we've just assumed P implies Q, which is equivalent to this. And so that becomes circular.
Okay, yeah, you're proving your assumption there.
Yeah.
Okay.
So this was a good homework set. I feel like people have got the idea. I got a coffee percolator, and my fiance just did a test run and left me a cup, and then she just put a note on top of it. So I'm gonna have to try it anyway. Yeah. So
Is it like a French roast or no French roast?
French press?
style?
No, it's an actual like old school percolator where you fill it with water, and the water steams and it goes up a little funnel, and that goes into a spout and comes down through a spreader, and that drips into the coffee grounds, and then the coffee comes out.
On TV or something.
Yeah.
I thought they were cool.
Yep. All right, but I gotta give it a try now because
Oh no.
I want to make that frowny face.
It's so bad.
It's. I
There's
won't
grounds in it.
look at that, man.
Oh yeah. Maybe right after the coffee filter.
Oh wow, it's super strong.
It's super bad.
It's just strong.
You think?
Yeah.
Okay.
I have not tried the AeroPress, but I think I may have had a student who had one. All right, so yeah, homework set, right? Despite losing some points here and there, I think people are basically on track with doing proofs. And it's not a course on proofs; it's a course on discrete structures. We're trying to learn the backbone material for kind of the theory behind what we do in our other programming courses. But I feel like people are successfully thinking through how you go from hypotheses to conclusion, and how you argue step by step and so on. These are details, right, that I'm picking out, but I don't want you to think from those that I have no idea how to do a proof or something. I think most people are almost there. The other thing was some of the proofs by contradiction. And we might have had this. There's something similar to that. If n squared is odd, then n is odd. And again, you don't want to start off by saying n is odd, because that's what you're trying to show. But if you start off, n is odd, and you do some other stuff, and you say therefore n squared is odd, well, that's a valid proof, and it's a true statement. If n is odd, n squared is odd. But it's not this statement, right? That's what we call the converse. And so if you're trying to show, if this, then that, you can assume this, right? So we could say n squared is odd, and then try to do some stuff and conclude that n is odd. And this was one of the problems where an indirect proof is a lot easier. And so an indirect proof, we start off with n squared is odd, but we also assume n is even. And then we argue until we get to our contradiction. At which point we say, I guess n cannot be even, so n must be odd. And then you're done.
Can you give us an example of that, just to kind of refresh my mind?
So let's do the full
You're
proof.
essentially converting it just by flipping the conclusion. You're essentially converting it to question 3 or whatever it was.
Basically, yeah. So n squared is odd, that's the hypothesis. Let's do not n is odd. That's the negation of the conclusion. So we're assuming this is true, but this is not true, right? Which means n is even. Which, follows from step 2. If it's not odd, it's got to be even. And so there's some integer such that n equals 2k. That's the definition of even. And now we can say n squared equals 2k squared equals 4 times k squared equals 2 times 2k squared. And that's substitution and algebra. But since we just show that n squared is 2 times an integer, that means n squared is even, and that's a contradiction. Because we also know n squared is odd. Therefore, this thing that we negated must in fact have been true, and so n is odd. And that's where you can say QED, because that's what you're trying to show, n is odd. All right, other questions around that?
Well, I have a question about that actually. That kind of went to my head. How does proving n squared is even make that n is odd? Because I don't really see how that really proves it.
So, proof by contradiction. Let's see. We know that n squared is odd. That's our hypothesis. Right? We're trying to show if this is true, then n is odd. So we're starting off by saying, okay, suppose n squared is odd. What we're basically saying is if n is not odd, if this is wrong, then we get a contradiction. Because we can eventually show that n squared is even though we know n squared is odd. So assuming this leads to a contradiction. It leads to false being true. Which means this must not be true.
Okay.
So it's kind of a backhanded way of proving this.
So you kind of just proving the opposite. If the opposite is true, then if the opposite is true, then that original statement should also be true. Is that what you're trying to say?
So by opposite, you mean converse?
Yeah. Well, I was trying to think of like you're trying to negate the conclusion. Is that negate the conclusion? So that way you can prove that you can prove that I don't know. I can't really think of words in my head right now.
Mm-hmm.
Yeah, I think I can see how the contradiction can be like kind of a different direction how to prove something, but it's just weird to me. That's all.
It is weird. So let's do this. Let's make this proposition P, and let's make this proposition Q. And don't do this on a test. Keep writing out. Let P be the proposition. But to work with what we got, let's make this proposition P and this proposition Q. Okay. So we're assuming P, right? And we're assuming not Q. And we're basically showing if P and not Q are both true, then we have a fallacy, right? But don't think about it like that. Think about it, if P is true and not Q is true, then something ridiculous happens, right? Which means if P is true, this can't happen. Q cannot be false. Because if it is, the universe breaks. So if P is true, the only possibility is Q has got to be true also.
Okay, that makes sense.
But we could also think of this as a direct proof, right? If we ignore all of this and we just start from here on down, we said suppose n is even. Okay, in other words, we started with not Q, and we argued and we argued and we argued and we came up with n squared is even, which is not P. So we actually, this part from here on down is a direct proof of this. If not Q, then not P.
Gotcha, then.
And so once we've proven that, well, this is logically equivalent to if P, then Q. Because that's the contrapositive of that. So this is actually a direct proof of this, which is the contrapositive of this. So it proves this also. But we usually think of it in terms of negating something and then finding a contradiction. All right, I'm done with my lunch. I got my camera back on. So let's talk about the midterm. I don't know if I talked about this last week. I think I probably did, but let me just give you a reminder. So midterm is on Wednesday. You will have the full hour and 35 minutes for the exam, so 12:30 to 1:55. I will plan on it being like an hour midterm, but you can have the extra half hour. And it's during class time, right? It starts at 12:30 and it ends at the end of class, unless you have an extended time allowance, in which case you have your extended time. Most of you people in here are also in 224, so you know how this works. But if you're not, the exam will open up on Canvas at 12:30. It'll be a PDF file that you can look at on Canvas, and it'll have a series of questions. To submit your exam, you basically write up the answers to those questions, save them as a PDF, and upload it to Canvas. Alright? If you've never done this, if you're not in 224, if you haven't turned in homeworks here, right, make sure that you know how to write something up either on paper or by typing it, turn it into a PDF, and upload that. Okay, don't try to crack that nut on Wednesday. Figure it out ahead of time. And assuming you've been doing the homeworks, right, it's basically like turning in your homeworks. Canvas will not close out at 1:55. It'll stay open. You can submit after that. If you don't have extended time, it'll be considered late, and it's 10 points per minute for being late. So make sure you turn it in before the deadline. There'll be an honor statement in the beginning of it that you need to read, and then to agree to it at the top of your submission, just write the words honor statement, : and put your name after that. Right, and that indicates your agreement. And the honor statement basically says, you know, you can use your notes, you can use the textbook, and nothing else. All right, so no online resources, no help from anybody, and no offering help to anybody else. So
What
pretty.
about a calculator?
You can use a calculator, yeah. I don't think you'll need one, but it never hurts to have one.
Thought I would for basically the modular exponentiation.
Oh, yeah. All right. Questions about the midterm? It's going to be basically like homework questions.
Can you give us a hint on how many questions will be?
I can't because I don't know. I got to write it up this afternoon. Several questions, probably. I mean, we've covered a bunch of stuff. So set theory, propositional logic, number theory. I think those are the main three things we've gone through. Page formatting. I'm going to ask you to try to work as neatly and as well organized as possible. So don't lead me on the goose chase, you know, across your page and over to another page 3 pages later and so on. Try to lay it out neatly, right? But it's a timed exam, so I'm not expecting people to work out their answers and then rewrite them, right? Which you can do on homework. But try to be reasonable, right? If you need to change an answer, don't you know, don't do something like this, you know. You know, don't change your union symbol to an intersection symbol like that. Draw a line through it and rewrite it. You know, make sure that I can read it and that there's no ambiguity when I'm trying to grade, basically. But you know, I understand it's a time situation, so I'm not going to be too worried about it. But try to work methodically. Try to make sure I can follow your work, and that I can find your answer if there's, like, you know, a single answer to a question. Make sure I can find that.
So is it just an hour and 20 minutes, so from 12:30 to 1:50?
Yeah, technically our class goes till 1:55, so an hour and 25 minutes.
Okay.
But I end my classes early on Monday because I have another class at 2. But yeah, so you got till 1:55. Any questions on the current homework set, which you won't be turning in until Wednesday, so you won't get feedback on that, but GCDs, modular exponentiation, things like that. Yeah, there is a difference between Fermat's little theorem and Fermat's last theorem. Fermat's last theorem we introduce in here just as, you know, an interesting historical, very complex problem, which was this question of, can you solve this in integers for n bigger than 2? And other than that, and the fact that, you know, it pops up in Star Trek episodes and stuff, we don't really do a whole lot with that. So that's Fermat's last theorem. But Fermat's little theorem we do use, which is this idea that a to the p minus 1 is congruent to a mod p. Sorry, congruent to 1. double check my notes on spacing. Yeah. And that's one way that we can do fast exponentiation. On Canvas, attendance is weighted at 0%. I assume it's supposed to be 10%. Really? Yes, attendance is supposed to be 10%. I thought it would yell at me if those didn't add up, but maybe not. Well, send me an attendance ping while I'm looking at this anyway. See, we got 20, 25, 45, 60. Oh man, my numbers don't add up.
You're gonna lower my grade.
Alright, I have to go back and look at the syllabus and see what I set that up for.
On the homework we did write numbers as product of powers and prime numbers.
Mhm.
Is there a faster way to do that than to just break it down?
For us,
by two
for that homework, I really just wanted you to kind of like trial and error it. Alright, so we're supposed to be doing homework 20, programming assignments 10, attendance 10, midterm 25, final exam 35. So let me adjust that right now.
I thought the final was worth 40%.
It says 35 on the syllabus.
Nice.
So attendance 10%. Homework is
Midterm and finals being worth 50 or 60% grade is how you're in a STEM class.
yeah. Programming. Okay, so programming assignments are only worth 10%, which is good. And then final is worth 35. Alright, that should add up to 100. Alright, and then there was a question on the homework. Let me scroll back through. Question 1. So determine what the following numbers are congruent to in the mod indicated. So so let's just do the first one, right? 26 is congruent to what mod 8? So the goal is to write 26 as something times 8 plus a remainder. So 26. So the informal way is, divide 26 by 8, see how much is left over. But that doesn't work as well when we have negative numbers. So we want to write 26 equals, something times 8 plus something, right? This is going to be your answer right here. As long as it's bigger than or equal to 0, and in this case, less than 8. We don't really care about the quotient, right? But 26 is something times that moduli 8 plus something left over. So how can we write 26 in terms of something times 8 plus something left over? Well, 26, can be written as 0 times 8 plus 26 left over. But that's too big of a remainder. It could be 1 times 8 plus 18 left over. It could be 2 times 8 plus 10. It could be 3 times 8. plus 2. It could be 4 times 8 plus negative 6, and so on. But among all of these, we want to pick the one where the remainder is not negative, but is also less than 8. And that's this one right here, and there's the remainder. So we would say 26 is congruent to 2 mod 8. So that would be your answer for part A, and it's the same thing for the other parts.
Can I ask you, because D, that one has a smaller number, and it's asking for what's congruent to that.
Mm-hmm.
I mean, we pretty much evaluated the same way.
Yeah, it's exactly the same question.
Okay.
So let's play with a similar but different question. Let's say 5 is congruent to what? Modulo 117. So we want to write 5 equals something times 117 plus something, and we want this to be bigger than or equal to 0 and less than 117. So how can we write this as something times 117 plus some small positive number?
0 times 0 plus 5.
0 times 117 plus 5. This is bigger than or equal to 0. It's less than 117. That's your answer. 5 is congruent to 5.
Okay. And that's kind of I guess, a theory, right? Is anything lower than the mod is itself?
Yeah, exactly.
Okay.
But not when you get to the negatives. So negatives, you have to kind of work through the same thing. Cool.
Thank you.
Yeah, you're welcome.
I'd like to go over 5, just to make sure I get it right. I missed that portion of class when I watched the lecture last night, but I just want to make sure I'm doing modular exponentiation correctly.
Okay, so I don't want to do that one in class, but I'll give you a choice. We could do a different modular exponentiation example in class, or you can come to office hours and show me what you did for that particular problem, and I can tell you how it looks.
Happy to do a different one.
Okay. So let's calculate 7 raised to the, I don't know, we'll go to the 100th. And let's go modulo 13. I don't know if that'll work out well or not. Alright, so first thing we do is we calculate powers of 7. We calculate 7 raised to powers of 2. So 7 to the first is just 7. Modulo 13. 7 squared we know is 49. And 49 mod 13, so we've done question 1. We're good at finding these moduli, right? 13 times 3 is 39. So 49 has 10 left over. I'm going to square both sides and say 7 to the 4th is congruent to 10 squared, which is 100, which is, maybe I'm not so good at modular math, I think that's 9 more than 91. But let's cheat. So 7 times 13 is 91, so 100 is 9 more than that, so this is congruent to 9. Square both sides, 7 to the 8th is 81, right, 9 squared. And 81 looks like it's going to be 6 times 13 should be 78. 81 is 3 more than that. So 7 to the 16th will be congruent to 3 squared, which is 9. And now we got a little pattern going. right? And I know that if something's congruent to 3, its square will be 9. If it's congruent to 9, its square will be 3. So let me squeeze my last one in here. This will be 3 squared, which is congruent to 9. So now I've got my table of 7 raised to powers of 2. And now I think about binary and I say 100 equals 64 plus 32 plus 4. So I've written out as a sum of powers of 2. And so 7 to the 100 is 7 to the 64 plus 32 plus 4, which is 7 to the 64 times 7 to the 32 times 7 to the 4th. It's the law of exponents. And so if I work with congruences, 7 to the 100th will be congruent to whatever 7 to the 64th is congruent to, times 7 to the 32nd times 7 to the 4th. Well, 7 to the 64th we already found was congruent to 9, 7 to the 32 is congruent to 3, and 7 to the 4th is congruent to 9. Now I could multiply this on a calculator and divide by 13, but I'm going to do 9 times 3 is 27 times 9, and 27 is 1 more than 2 times 13, so 27 is congruent to 1, and that's still 9, and so this whole thing should be congruent to 9. And so that should be my final answer. And then we can check it. So there's 7 to the 100th. And if we do 7 to the 100th minus 9, we get this. And if we divide by 13, it's a whole number with a bunch of zeros. So yeah, 7 to the 100th is...
To do the last one, to double check, I had to go find a calculator online.
Yeah.
That did that big of numbers.
Mm-hmm.
Just to see if I did it right.
Right. Yeah, and there's no slick shortcut for that I know of. But if you got a Unix machine, BC is usually built in, and BC-L will do arbitrary precision. 7 to the 10,000 will take it a while, but it will get there eventually. It doesn't take it that long, actually. So this will do arbitrary precision and arbitrarily large numbers.
What is arbitrary precision?
I meant arbitrarily large numbers.
Oh.
So it's not limited to 2 billion or 10 to the 99th or something, because it can chow on numbers that big.
And just to be sure, I'm pretty sure I did it right, but I was able to do number 6 in like 6 steps.
Yep.
That should be the case, right?
Yeah, number 6, Fermat's little theorem, doesn't take nearly this much work. It's a lot shorter.
Yeah, I noticed it was a lot easier.
Yeah.
Which is pretty cool.
It's a lot easier, but it doesn't always apply as easily. Modular exponentiation is very sort of programmatic. We can always go through these steps and get the answer. Fermat's little theorem is taking advantage of certain cases where, for example, that 6002 is just a little more than a multiple of 6. And that's what makes it work.
Do we have to say mod 13 by every one of those statements for that to be correct?
No, you can see I started getting relaxed with that. So as long as you sort of put it once, if you say congruent with the triple equal sign, we'll just assume it's the same moduli. But the triple equal sign is important, right? I can't write 100 equals 9 because that's not true. But I can say 100 is congruent to 9. And to talk about congruence, you need to know what modulo in, well, the last one I mentioned was 13, so that's just going to be, through all of those. All right, good enough? So let's go back to mathematical induction. And you know, clearly this is not part of the midterm, but this is important stuff in general and in life. And so I gave you kind of a hand-wavy introduction to this on Friday when we talked about having an intuition for how to do something in general. And I said mathematical induction will let us make a very precise presentation of that intuition. So let me give you the exact statement of mathematical induction, and then we'll start applying it in some situations and see how this works for us. So the process of mathematical induction, it's a proof technique, and it involves two steps, and these are called the basis step and the inductive step. Okay, the basic idea though is approximately this. So we're given a family of propositions. For example, P1, P2, P3, right? Pn, where n is an integer and n is bigger than or equal to 1. Now we can wiggle this around. We could have a family of propositions starting from P0. We could have a family of propositions for even integers bigger than or equal to 6, right? But the general setup, the most common setup, would be a family of propositions, P1, P2, P3, and so on, where the number in here is a positive integer, so bigger than or equal to 1. And a family of propositions, remember, means this is a proposition, this is a proposition, this is a proposition, right? Each of these is an individual proposition. And your goal is usually to prove that P of n is true for all n bigger than or equal to 1 in this case. In other words, to prove that every proposition in this collection of propositions is true. Okay, that's the goal. And let me give you an example of such a family. Let P of n be the proposition. Let's say now we don't like using dots in mathematics because it's imprecise and it can lead to things, but to write this more generally without the dot would end up taking us down a different path. So I'll trust you understand what I mean by this. If I take the union of n sets and then I complement it, I should end up with the same thing as if I intersect the complements of those sets. This is De Morgan's theorem for sets. And Pn is the proposition that this works for any n sets, S1 through Sn. So for example, P of 2 is the proposition S1 union S2 bar is the same thing as S1 bar intersected with S2 bar. It's plain old De Morgan's theorem. But P of 3 is the proposition that if we generalize this to 3 sets, it still works. And I think we might have shown this when we were playing around with sets and properties of sets. And if you know De Morgan's theorem works for 2 sets, you can show pretty easily it works for 3. All right. Well, we have a whole family of propositions: P1, P2, P3, P4, P50, P605, right? And each of those is a proposition that by itself could be true or false. Okay? So suppose we want to prove that all of these propositions are true. And P1's a little weird because it says, you know, the complement of S1 is the complement of S1, but don't worry about that. We want to prove that all of these propositions are true. In other words, we want to prove De Morgan's theorem works in general for any collection of n sets. If you take the union of all n and complement it, it's the same as intersecting the complements of each of those n sets. So that's our family of propositions. Our goal is to prove P of n is true for all values of n. And mathematical induction tells us we can do this if we can do the following two things. So 2 steps. This is for mathematical induction. Step 1, prove typically P of 1. Right? Prove that some initial member of this family of propositions is true. Well, what is De Morgan's theorem on one set? It's kind of trivial, right? It just says, you know, S1 bar equals S1 bar. But so maybe this isn't a good example. I'll start with 2. We'll work with it. So step 1, prove P of 1. Okay. Step 2, a single thing we have to prove. Prove that if proposition n is true, then proposition n plus 1 is also true. According to mathematical induction, if we can prove that P of 1 is true, and we can prove that Pn gives us Pn plus 1, then we can conclude P of n is true for all n bigger than or equal to 1. That's the mathematical induction part. All right, so let's think about this. We're trying to prove P1, P2, P3, P4, P everything is true. I'm claiming we don't have to prove all of these cases. We can do the following. We can prove a single case, such as P1, and then we can prove this very, very particular thing, which is if Pn is true, so is Pn plus 1. If we do both of those, then we can say, therefore, by mathematical induction, P of n is true for all n. All right. So let me shift gears slightly and let's do a slightly different version of this. Remember I said we can wiggle this around a little. Let's prove this family of propositions, right? Let's prove P of n for all n bigger than or equal to 2. So we won't worry about De Morgan's theorem with one set. So P2 is the proposition that this is true, P3 is the proposition that that is true, and so on and so forth. We might be able to prove each of these propositions individually, but the only way we could prove that this is true for all n is to show that, you know, for every n this is true. So I might, you know, prove P2, P3, and P4. What about P5? Well, I could set n equal to 5 and write this out and show that this is true when you have 5 sets. But what about P6? So there's an infinite number of propositions to prove. Mathematical induction claims that I can do the following. If I can prove P of 2, and if I can prove P of n implies P of n plus 1 for any n bigger than or equal to 2, then I can conclude P of n is true for all n bigger than or equal to 2. And does everybody see the difference between this and that? This is a single proposition I'm trying to prove. This is an infinite number of propositions I'm trying to prove. Everybody okay with that?
Is that kind of, it's proving one proposition, but isn't it kind of predicated on proving p to the n at least once, so it's 2?
Mm-hmm. Yeah. And this is really, it's about the chain rule, right? If I prove these two things, can I prove that P of 5 is true? Absolutely, I can do it with no real work. And here's how I do this. I say P of 2 is true. And since P of n implies P of n plus 1 for all n, if I just set n equal to 2, this statement implies P of 2 implies P of 3. Well, since P of 2 is true, and if P of 2 is true, P of 3 is true, that gives me P of 3. Well, if I set n equal to 3, this statement says P of 3 implies P of 4. So use detachment again. P of 3 is true, P of 3 implies P of 4. That proves P of 4. And if I let n equal 4, this says P of 4 implies P of 5. Use detachment one more time. P of 4 is true, P of 4 implies P of 5. Therefore, P of 5 is true. And
So we just have to do that singular proof to plus prove that
yep,
the first step is true, and then we know that this infinite proof is true.
exactly. If I can prove these two things, right, common sense says I can keep doing this 100 times and I can prove P of 102 is true, right, or 1,000 times or 1,000,000,000 times, right? So mathematical induction is sort of our go-to when someone says, well, how does this prove that P of 5 is true? We don't have to do this. We can say mathematical induction, talk to my friend. So our whole problem of proving this infinite family of propositions is true will be simplified to proving just two things. So if we work with this family of propositions, where P of n basically says, this is equal to that, well, how do we prove P of 2? That's De Morgan's theorem. And assuming we trust De Morgan, we can just say, this is true because De Morgan's theorem says it is. And now we have to prove if this is true for n sets, it's true for n plus 1. And that's actually not too bad to do. So let's prove P of n implies P of n plus 1. This is for some integer n bigger than or equal to 2. So step 1, P of n, that's our hypothesis. Step 2, S1 union S2 union everything else out to Sn is equal to this. That's the definition of this family of propositions. All right, step 3. So here we're gonna do this with some other examples, and we'll set up an ignore section and so on. But we're still kind of at the hand wavy sort of higher level view of this. The idea is, if I know that De Morgan's theorem works on two sets, those sets could be anything, right? So in particular, I can make the following statement. This thing, union that thing. This is a set, right? It's a union of n sets, but this is a set, this is a set. I take their union and I complement. De Morgan's theorem tells me that I should get the inverse of this first thing. intersected with the inverse of the second thing. Alright, that's just plain old De Morgan's theorem. But I also know that this is equal to this, because that's the second proposition I wrote. So this thing is equal to this intersection, and I'm still going to leave this intersection of Sn plus 1 complemented, right? And that's just substituting from step 2. Well, what did we just show? We showed that the complement of the union of n plus 1 sets is equal to the intersection of those n plus 1 complemented sets. Well, what is another name for that proposition? That's just P of n plus 1. Because P of n plus 1 would be the proposition that if we take the union of n plus 1 sets and complement, that's the same as intersecting the complement of all n plus 1 sets. Well, that's what we just showed. This union is equal to that intersection. So we just proved P of n plus 1. So therefore, P of n implies P of n plus 1. There's our inductive step. So P of 2 is true because that's De Morgan's theorem on 2 sets. P of n implies P of n plus 1 because we just proved it right here. Therefore, by mathematical induction, P of n for all n bigger than or equal to 2. All right, so we're going to do some other examples of that, but let me name these steps. This is called the basis step, or sometimes a base case. This is called the inductive step. And we're going to encounter these a lot through the rest of the course. And we're going to encounter them a lot in CSE215. Where did the Sn plus 1 come from in step 3? Nowhere. I just decided to take this union and add that thing to it. Right? I just pulled it out of thin air. But I can definitely assert that this is the same thing as this. Right? Because De Morgan's theorem tells me this union, this complement is the complement of this intersected with the complement of that. So this was just a statement of De Morgan's theorem. But how did I know that I should take the union of Sn plus 1? That's where the intuition is going to come into. That's where putting an ignore section on the side of our page and playing around with things and thinking about what we're trying to get to is going to help us say, oh, you know what, I should take the union of this with Sn plus 1 and then apply De Morgan's theorem. And a funny thing about proofs, well, funny, strange, not haha, is if you follow the steps of a proof from beginning to end and each step is logically correct, you're forced to accept the final conclusion of the proof, even if there's no clear indication of why the person's going from one step to another. As long as each step is justified as to why it's true, there doesn't have to be any intuition as to why you're doing this and why are you doing that, right? And this is a kind of cagey area in mathematics. There have been cases of sort of natural-born mathematical geniuses who came up with fantastic proofs that had no like rhyme or reason to why they were doing this, but they led to, you know, an irrefutable conclusion. But people got upset about this and questioned whether this was a valid proof because they were doing things in the proof that there's no reason for doing this, but all of a sudden at the end, you know, something pops out. And so this may feel a little bit like that to begin with, but we're going to work with some more mathematical algebraic examples next, and we'll see, you know, better sort of where to make this leap. But in general, our proofs are going to kind of have this split aspect where the stuff in the beginning of the proof is going to be, stating the hypotheses, writing down the definition of one of these propositions and so on and so forth, all this kind of preamble stuff. And then there's going to be some little spark of insight somewhere where we're going to do something, and then everything after that's just going to be kind of like paperwork leading up to, Pn plus 1, therefore Pn implies Pn plus 1, etc. So just like with some of the proofs we were doing a couple of weeks ago, there's going to be this spot in the middle where something happens, and that's going to be kind of, the magic spot. All right, so we'll talk later about why this works, and why it works is a whole nother subject. But let's do some more examples. So let's look at sums of integers. So let P of n be the proposition 1 plus 2 plus 3 plus ... plus n equals n times n plus 1 over 2. Alright, it's a family of propositions. And I'm going to restrict this to n bigger than or equal to 1, because we got this ... thing, and if n was negative 5, it's not clear what this means. But for example, P of 3 is the proposition 1 plus 2 plus 3 equals 3 times 3 plus 1 divided by 2. Was P of 3 true or false? Awkward pause. So is 1 plus 2 plus 3 equal to 3 times 3 plus 1 divided by 2?
No. Because that would be 6, and then 3 times 3 plus 1 divided by 2 would be 5.
Let's see. 3 plus 1 is 4. 3 times 4...
6 equals 6.
Yeah, 3 times 4 is 12, divided by 2 is 6. That's the same as 1 plus 2 plus 3.
Okay, no, I messed that one up.
That's okay. So yeah, this is true.
So that's true.
P of 2 is the proposition 1 plus 2 equals 1 times 1 plus 1 divided by 2. Sorry, 2 times 2 plus 1 divided by 2. So that's 3, that's 2 times 3 is 6 divided by 2 is 3. That looks like it's true. P of 1 is kind of a silly proposition. It says 1 is equal to 1 times 1 plus 1 divided by 2. Well, that's 1 times 2 is 2 divided by 2 is 1, so that's true also. So the first few cases of n, it certainly looks like P of n is true. And so we could be asked to prove P of n for all n bigger than or equal to 1. And sometimes it's useful to, try a few of these and convince yourself whether or not this is even a reasonable thing to be trying to prove. And this looks reasonable, and you may, recall this formula from some other class, and we can generate this a number of ways by thinking about adding pairs of integers and so on. Some people use this on the CSE215 midterm. But how do we prove it, right? And it turns out it's pretty straightforward to prove using mathematical induction. There's some algebraic gymnastics we have to do, but it's a good example of this induction process. Alright, so we want to prove this for all n bigger than or equal to 1. So I'll leave the proposition up here. And I'll just say prove P of n for all n bigger than or equal to 1. And we're going to do it using mathematical induction. So we have to prove two things. The first is the basis step, which says we need to prove P of 1. And we already did that. We said P of 1 is a proposition that 1 equals 1 times 2 over 2, which is true. Shown on prior page. So P of 1 is true. When we just say, you know, P, the implication is P is true, right? All right, so P of 1 is true. So the real work comes in the inductive step. Prove that if P of n is true, then P of n plus 1 is true, where n is some integer bigger than or equal to 1. So we have to show that for any integer n bigger than or equal to 1, if P of n is true, then P of n plus 1 is true. But it's still just a single proposition to prove. We get to imagine that n is some fixed number and say, hey, you know, for that value of n, is P of n plus 1 true if P of n is true? All right, so let's prove this using the kind of proof machinery we've been doing. So step 1, we're going to assume the hypothesis, P of n. That's the hypothesis. Step 2, I'm going to write out what P of n is, right? Which is this statement right here. 1 plus 2 plus everything up to n is equal to n times n plus 1 over 2. And that's the definition of P of n. All right, here comes the intuitive spark, right? That we'll need to develop through practice, but a lot of times it'll look exactly like what we're doing here. We've only got 2 minutes left, so I'm just going to add n plus 1 to both sides of this, right? That's perfectly legal. If this is equal to that, this plus 5 is equal to that plus 5. That's guaranteed, right? So I'm going to say 1 plus 2 plus everything up to n plus n plus 1 is equal to n times n plus 1 over 2 plus n plus 1. And my reason? Adding n plus 1 to both sides. And this is not violating something I said a few weeks ago about being careful about manipulating both sides. That was a caution about trying to claim that if two things are equal, then somehow we've proven something earlier in our statement, right? That's not what we're doing here. We're just saying this is equal to this, so this plus n plus 1 will equal that plus n plus 1. But now I'm going to go a little wild with the algebra and say this is n squared plus n divided by 2 plus n plus 1, which is equal to n squared plus n plus 2n plus 2, all divided by 2. So I changed this into 2 times n plus 1 divided by 2 and brought that down on a common denominator. And this is n squared plus 3n plus 2 divided by 2. And then I'm going to factor and say this is n plus 2 times n plus 1 over 2. And that's all like algebra with an exclamation mark. Now why I chose to do that, that's something that we're going to have to develop over time. But again, for whatever reason, I decided to add this to both sides, and then I did some algebraic manipulations and rewrote this in this form. But guess what I've got now? Over here I have the sum of the integers from 1 to n plus 1, and over here I have something that looks very much like this. It's actually n plus 1 times n plus 1 plus 1 divided by 2. So this is exactly the statement P of n plus 1. And if you go back and think about what P of n plus 1 says, it says the sum from 1 through n plus 1, that's that, should equal n plus 1 times n plus 1 plus 1 divided by 2. So we've proven p of n plus 1, so let's just wrap this up. So step 5, so I would say therefore p of n implies p of n plus 1. Well, we've proven p of 1, and we've proven p of n implies p of n plus 1. Therefore, p of n for all n bigger than or equal to 1. And the reason for that is mathematical induction. And that's what we were asked to show. We were trying to show p of n for all n bigger than or equal to 1. That's what we just ended up with. So that's an example of a proof by mathematical induction. So you know, midterm is on Wednesday. We'll come back to this Friday, so that's going to be a few days away. So we'll review this completely on Friday. We'll work through this and maybe write it up a little differently using summation symbols, just for practice with that. And then we're just going to start doing a bunch of examples. And we'll do examples that are algebraic in nature. We'll do examples that have to do with physical things. We'll have examples that have to do with thought exercises, and a whole bunch of different applications of this. And we'll just keep hitting it Friday and a good part of next week, and messing around with this. And we'll build up some intuition around it, and we'll post some homeworks next week. I probably will not post new homework this week because, you know, midterm and stuff. All right, cool. Have a good afternoon then. I will see you in 224 tomorrow if you're there. If not, I will see you Wednesday. Definitely hop into Zoom during the exam so I can announce corrections and clarifications. Try to get here on time, 12:30 to 1:55 plus extended time if allowed. Shoot me an attendance ping on the way out. Have a great afternoon, and I will see you next time.
Goodbye. See you.
See ya.